the lipid chain. So, lipids and carbohydrates are made up of the same basic things: carbons, hydrogen, and oxygen.
So let's get a little more familiar with lipids. There are 3 types of lipids: triglycerides, phospholipids, and sterols. Every lipid is made up of fatty acids. There are 2 types of fatty acids: saturated and unsaturated.
When something is saturated, it's got as much of something as it can stand, right? When a fatty acid is saturated, it's got as many hydrogens as there are places for hydrogens to go. The fatty acid is saturated with hydrogens. It's completely hydrogenated. Now, when a fatty acid is missing a hydrogen or 2, it's not as hydrogenated as it could be, and we say it's an unsaturated fatty acid.
3 terms designate the degree of saturation in food fats: saturated, monounsaturated, and polyunsaturated. Let's take a closer look at these 3 degrees of saturation.
First, saturated fats are fats composed of saturated fatty acids. What are they saturated with? Hydrogen, that's right. These food fats mostly come from animals. Second, monounsaturated fats are made up mostly of fatty acids with 2 less hydrogen atoms making 1 double bond. These come mostly from plant sources. Olive oil is an example.
Third, polyunsaturated fats are made up mostly of unsaturated fatty acids with 4 or more places unfilled with hydrogen atoms creating double bonds. These fats come from plants like safflower and sunflower oils. No one fat type is 100% saturated or unsaturated. It's a combination of poly, mono, and saturated fatty acids.
Fats shouldn't supply more than 25% to 30% of the body's well-balanced diet. About 2/3 of these should come from unsaturated fats, or vegetable oils, rather than animal food products or saturated fats.
Remember, all types of fat still have 9 kilocalories per gram, but different types of fat have different effects on blood cholesterol. And depending on the person and their needs, this can be good or bad. If you get more than 10% of your daily calorie intake from saturated fat, the amount of total cholesterol in your body will go up, plain and simple.
Monounsaturated fat should have a minimal effect on total cholesterol in a diet with a 10 to 15% intake of it. If a diet has more than a 10% intake of polyunsaturated fat, it may actually decrease the total cholesterol.
Okay, so now that we know what fats are, let's look at how they're broken down in our bodies for digestion.
All fats have the same basic structure: a fatty acid attached to a glycerol base. You don't need to worry about what a glycerol is. Just know that it's an anchor of sorts that holds fatty acids. If there is one fatty acid attached to a glycerol base, that's called a monoglyceride. If there are 2 fatty acids, it's called a diglyceride. And when a glycerol is attached to 3 fatty acids, you guessed it, it's a triglyceride.
Fat digestion is the process of changing basic fuel fats, like butter, into refined fuel fats that can be burned by the cells for energy. This just means that a food source like fat is broken down to a simpler form like fatty acids. There are several steps in the fat digestion process.
The fat digestion process begins in the mouth, where fat is broken down for passage into the stomach. This is not really a chemical process. You just chew your food into small particles and moisten it for its journey.
The next step in the fat digestion process occurs when the fat hits the stomach. There isn't a whole lot of chemical breakdown of fat in the stomach either. The involuntary act of peristalsis, involuntary muscle contractions, breaks down the fat somewhat. Lipase is the only enzyme in the stomach that specifically breaks down fats. It works on butterfat. While other nutrients of the food mix are broken down by enzymes, fats are separated and made more accessible for the small intestine, which is where the real action is.
The last step in the fat digestion process is when the fat reaches the small intestine. Once fat reaches the small intestine, it begins the process of being chemically broken down. A lipase, which works on emulsified butterfat, breaks apart the triglyceride, separating the fatty acids from the glycerol. Now the fatty acids and the glycerol are small enough to be absorbed. Then, enzymes carry the fat into the walls of the small intestine to begin the process of absorption.
But that sounds easier than it actually is. Fats are difficult to absorb into the bloodstream because they're not soluble in water, and blood is mostly water. Fat, therefore, always needs a solvent carrier. We'll explain soon.
Once in the small intestine, fat is chemically broken down by bile and pancreatic lipase. Let's look at each of these substances and what they do.
First of all, bile is produced by the liver. Once manufactured by the liver, the bile is sent to the gallbladder, which secretes the bile into the small intestine. Bile is an emulsifier. Great, so what does that mean? Well, basically, as an emulsifier, the bile takes the fat that's floating around in the small intestine and breaks it down into smaller chunks. It's important that you realize that this is not a chemical process. The bile isn't digesting the fat or anything, it's just breaking it down into smaller and smaller pieces.
By doing so, the surface area of the fat in the small intestine is increased, giving the enzyme that eventually digests the fat more of a surface area to work with.
Once the fat has been broken down into smaller and smaller pieces, it's time for digestion to begin. The pancreas manufactures and secretes the fat-digesting enzyme pancreatic lipase. Let's see what happens to a triglyceride that finds itself in the small intestine. Remember from earlier that we told you a triglyceride is a glycerol base with 3 fatty acids attached. The pancreatic lipase then breaks off one of the fatty acids, turning the triglyceride into a diglyceride. The pancreatic lipase then breaks off another fatty acid, converting our diglyceride into a monoglyceride.
Eventually, although it's a pretty slow process, the last fatty acid is broken off and we're left with a lone glycerol. This happens with all the fats that are brought into the body, and we end up with a bunch of fatty acids and glycerols in the small intestine.
Okay, so what's next?
Next, the bile joins up with the newly broken down fatty acids and glycerols and carries them into the wall of the small intestine. Here, the bile drops off the fatty acids and glycerol and says, "See ya!" It heads for the bloodstream where it's taken to the liver and the whole process starts over. Meanwhile, we've got these fatty acids and glycerols sitting in the small intestine. And here's the cool part. There are all these different types of fats that we eat and bring into our bodies, from animals, from plants. Here's where all those different fats are converted into the fat that's used by our bodies. In the wall of the small intestine, the fatty acids and glycerols join back up and make triglycerides, human body fat. Once the triglycerides have been synthesized, they're faced with a bit of a dilemma. Have you ever tried mixing oil and water? It's pretty much impossible because fats are insoluble in water. They won't touch the stuff. That's a problem though, because the triglycerides sitting in the wall of the small intestine need to make it into the bloodstream so that they can be used by the body, and blood is mostly water.
There's no way the triglycerides are going to leave the comfy wall of the small intestine and head for the hills. I mean blood. Something must be done. So, the triglycerides are surrounded by a group of water-soluble proteins. When this happens, they form a spherical complex called a micelle. A micelle carries about 20 fatty acids and monoglycerides into intestinal cells. Now that the micelles have helped them into the intestinal cells, the monoglycerides and fatty acids are reassembled into new triglycerides. Now, these brand new triglycerides and other large lipids are packed into another vehicle called a chylomicron. This protein triglyceride complex is the vehicle that transports lipids from the intestinal cells into the lymph system and eventually into the bloodstream to be put to use by the body.
Chylomicron. This is one popular vehicle. Now, I don't know if you have any triglycerides or large lipids running around at home. I know I do. This baby can sure pack them in. She is a beaut.
By the way, a similar thing happened when the broken down fatty acids and glycerols were sitting in the small intestine. Without getting into too much detail, the fatty acids and glycerols are not only insoluble in the water that's in the small intestine, but they're also repelled by the wall of the small intestine. That's why the bile formed up with the fatty acids and glycerols to carry them into the wall of the small intestine. This is called a solvent carrier system. Now, let's look at the option of fat replacements in our diets.
Food manufacturers are struggling to produce fat replacements that imitate the creaminess and taste of fat without the K-calories. Most of the fat replacements under development are based on one of the 3 energy-yielding nutrients: carbohydrates, fats, and proteins. Carbohydrate derivatives such as dextrins, which are modified food starches and gums, have been used for years as thickeners and stabilizers.
The U.S. Department of Agriculture developed another carbohydrate-based fat replacement called Otrim from oat fiber. This type of fat replacement can generally be used for baking, but not frying. It can be found in margarine, frozen desserts, and salad dressing.
Olestra is a recently released fat-based fat replacement that is kilocalorie-free. It is indigestible and cannot be absorbed. Olestra carries some fat-soluble substances out of the body. Basically, fat-soluble just means anything that dissolves in fat, like cholesterol and some vitamins. This may result in lower blood cholesterol, but has the potential to interfere with fat-soluble vitamin absorption, like vitamin E absorption. This happens because the vitamins attach to the fat, thinking they're taking the express train to storage, you know, body fat. Fact is, they're on the express train to the toilet.
Simpless, however, is a protein-based fat replacement that was approved for use in 1990. It cannot be used for baking and frying. It is often used in frozen desserts.
The concern with fat replacers is that consumers will use them in addition to other fats rather than in lieu of other fats. If used properly, they may help individuals lower their fat intake while still enjoying the flavors and textures previously reserved for high-fat foods.
Negative effects of fat replacers when eaten in excess include abdominal cramping and diarrhea. That's just what happens when you try to beat nature.
Okay, it's time to step back and see what we remember about fats. First off, another word for fats is lipids. There are three basic functions food fats perform in our diets. First, they are a fuel source for energy. Second, they supply essential nutrients to the body. And third, they add to food satiety. Tissue fats also have 7 more TEC-V10 functions in our body. Tissue membrane structure, energy, cell metabolism, vital organ protection, thermal insulation, essential precursor, and nerve impulse transmission. There are 2 types of fat, saturated and unsaturated. A saturated fat is a fat that is filled with as much hydrogen as it can take. An unsaturated fat is not as hydrogenated. Fat digestion mainly occurs in the small intestine. Bile and pancreatic lipase are the agents responsible for the breakdown of fat in our bodies.
Section C, protein.
As we said before, protein is a macronutrient that is energy yielding. Now let's take a closer look at this guy.
Amino acids are the building blocks of protein. Chemically speaking, they have a central carbon atom, C, with a hydrogen, H, an amino group, NH2, an acid group, COOH, and a side group. This side group or side chain is the only thing that changes in the chemical structure to make up one of the 20 common amino acids. That makes proteins more complex than either carbohydrates or lipids. Now you know why we saved them for last.
Like we said, there are 20 common amino acids, so the variety of possible sequences is enormous. Most proteins contain at least 30 amino acids, and some may have more than 300. Amino acids are connected to each other with peptide bonds. These amino acid bonds have names depending on the number of amino acids. A dipeptide is 2 amino acids bonded together, while a tripeptide is 3. A string of 4 to 9 amino acids bonded is called an oligopeptide, the prefix oligo meaning few. A group of 10 or more is called a polypeptide, the prefix poly meaning many. Polypeptide chains twist into various intricately coiled shapes.
So why is protein so doggone important? Well, proteins in foods supply the amino acids from which the body makes its own proteins.
Now that we know the structure of protein, let's see what happens to it once it gets into that remarkable body of ours.
Mechanical digestion of protein begins in the mouth where it is crushed and moistened, and chemical digestion begins in the stomach. Hydrochloric acid in the stomach changes protein strands in such a manner that digestive enzymes can break the peptide bonds that hold the amino acids together.
When polypeptides, which are 10 or more amino acids bonded together, enter the small intestine, enzymes hydrolyze them into shorter peptide chains. Enzymes that hydrolyze protein are called proteases. Remember, ase means enzyme. So just take the beginning of protein, prot, and add ase to get protease. A good example of a protease is pepsin, which is released by the stomach and begins to break down the protein into smaller units and amino acids. These cells absorb